Hi, Mark Palmquist here. Somebody asked me to do a quick video on how I designed my sail, and so I'm going to go ahead and do a video. Okay, first, what is the purpose of a sail? Most people have probably heard the purpose of a sail is to catch the wind. But a more accurate description of what a sail does is it temporarily changes the wind's direction. So if we look at the first phrase, catch the wind, we can illustrate that by drawing a parachute. A parachute is what catches the wind, and a parachute is designed to disrupt the airflow and to basically go against the current, the wind direction, and slow you down. There's another word for this, it's called drag, and if you look at the ideal shape for drag, it's basically a semi-spherical shape that's hollow, and it has an aspect ratio of 1:1. Aspect ratio is the proportion of its length to width. The other way to fall from the sky is with a sailplane. So with a sailplane, you're not catching the wind, you're deflecting the wind. You're temporarily changing the direction of the wind. And the angle, if you look at the cross-section of a wing, the angle in which the airflow hits is very slight. The angle at which this hits the wind is 90. So these are the two extremes. Drag is basically blunt, something blunt to the fluid flow, and lift, this is called lift. Lift is something at a very acute angle to the oncoming fluid flow. They both do the same thing. They temporarily disrupt the direction of the fluid, and they're both ideal in their own angle of attack. Okay, so the problem is with a sailboat, sailboats have to go in all directions. So sometimes the ideal angle of attack is downwind, and sometimes it's as high to the wind as possible if you're attacking into the wind. So if you take circle and basically this shape and you morph them together into one, you get something like this. So here's an aspect ratio of 1:1. Here's one, let's say 1 to let's say 20, and then if you morph these together, you get something like 1:6 or 1:8. So because a sailboat has to go, like a downwind sail, the ideal shape is basically a square or a circle, and upwind is like basically a wing that's long and narrow, and the ideal shape for a sail is somewhere in between. And when I say ideal, there is no real ideal shape for a sail because it depends on your heading, and that's why when you're designing a racing boat, sailboat, you usually have like 5 sails, and you change your sails based on your heading and the speed of the wind. Okay, so let's look at the first sail. The first sails were square. What happens when wind hits a square? The shape that you get when wind hits a square is basically something between a parabola and an arc. I forgot the name of it, but it's the same shape that, you know, when you suspend a rope horizontally, that's the shape. Gravity affects it. That's the shape. I forgot the name of that, but that is basically the shape. Now, what is wrong with this shape? This shape is really good for going downwind, but when you're at an acute angle and you're going fast, this shape is not very good for a sail because of the Bernoulli principle. Let's discuss that. Okay, so as air enters a narrow inlet, the air accelerates, and what has been observed is that this angle here, let's say 20 degrees, and this angle, if the air is flowing this way through the tube, these angles are not the same. The ideal angles are different. So the ideal angle for the exit nozzle is about half. So let's say this is 10 degrees. And the reason for that is just that's the quality of fluids. So as air enters, or any fluid enters a constricted space, it accelerates, it speeds up. And then once it's at, basically the speed is at its maximum at the tightest spot, and then it has to slow down. And if you make this angle as steep as the front angle, then you get waves in the flow, and you get turbulence, and this creates drag. And so to avoid that, there's something called the airfoil shape. And the airfoil shape is basically this, where the widest part of the foil is, if this is X front to back, this is 1/3 X. So with most now this also changes depending on how fast the object is going through the fluid flow, but in general, 1/3 from the front is the ideal, gives you the ideal shape for a wing. And basically a sail is a single-sided wing. So if you look at this, the fluid will go here and it'll be fine, and then it'll start detaching because of the severity of the angle. So that's just what you get out of a square. The other shape for a sail is a triangle. So the center of area of a circle is right in the middle. If you look at the center of area of a triangle, you find something really interesting. If this is X, then the distance to the center of area of a triangle is 1/3 X. So if wind is coming this way on a triangular sail, the cross section will be an airfoil just like this, because the air pressure will push the hardest in the middle of area. So a triangle is a much better shape than a square. However, a square is better in terms of surface area than a triangle. And also the thing about a triangle is the ideal airfoil shape is basically in the middle, and the closer you get to the top or bottom, if you look at the cross section here, let me get a new piece. All right, let's look at a couple different sails. Here's one sail, and here's another sail. Turns out that it doesn't matter where you put this point, whether it's here or down here, the properties of a triangle are the same. So it's always, the center of pressure is always 1/3 from the leading edge. So it doesn't matter if your sail is this shape or if it's this shape. A sail like this requires a spar to basically hold this point from sagging downward. And a sail like this requires a boom at the bottom. So you don't see a lot of sails that are like this with the bigger area at the top, because you would have to have some kind of spar up here holding it in place. And there's no way, it's hard to control this. How do you control this? Like, you'd have to have a line going way down here. So anyway, not a lot of people do this configuration. You'll see it in the Pacific Islanders. Some of them do this configuration. But these are the two main configurations that people do with a triangular sail. Let's look at the cross sections. The cross section in the middle is a perfect airfoil. And then over at the top, because this kind of tends to bend in a cylinder, if you look at the cross section at the top, it's like this. This is actually pointing directly into the wind. So there's the top corner and bottom corners of a triangle, you don't get any power at all. It's zero, because if you look at the angle of incident, it's basically zero. And if you get way up here, you can actually have a negative angle of incidence where it's actually slowing you down. So in general, this is the drive area of a sail. And the corners don't do anything. Same thing here. You're not going to have a lot of drive up here. This is not going to do anything for your speed. And it has to do with the cross section of the shape. It's not an airfoil up there. So what people do is they just cut the top off, and then you get basically a flat-headed sail. This is sort of in between it's not a square, it's a rectangle, but it's triangular rectangle. So this is kind of like halfway between the two. So when you have a shape like this, to get this to conform to the correct shape, you do it by how you cut the material and your seams, and you create three-dimensionality into a sail like this. And it's very high-tech, and you have battens. You have to have a batten here, and sometimes you have full-length battens. But a sail like this, to have a nice shape, requires some three-dimensional stitching. So that, like, let's say if you broke this into two parts, you'd have something like this. But anyway, I'm not going to get into that because that's overly complicated. Here's another type of sail. It's a triangular sail. It's called the crab claw. It's a little bit different from the other triangular sails in that the curvature is basically along this line. And you don't really have an airfoil anywhere where you have more of the same. It's an arc shape. But the difference here is the angle at which the air hits these spars is not perpendicular. It's at an angle. And so what you do is you get just like a paper airplane. All right, let's draw a paper airplane. Here's a paper airplane. There's no curvature on a paper airplane, but they fly. And the reason they fly is air slips around these edges and spins around like this. And you get these swirling vortices on the sides. And these vortices create low pressure on the top, and that's how this gets lift. So there's still a lot of debate on how a triangular Pacific Ocean lateen sail works. I don't really know. There's still debate about that. So I'm not going to talk about that, but I will talk about the lug sail. The lug sail is basically the same thing, but you're cutting off the front triangle, and you have a boom, and you have a yard. And this has to extend, and this mast extends up here, and it holds the yard. So this is a lug sail. It's basically a truncated triangle. The front is cut off. And one of the secret ways to improve a triangular sail is just to cut off the corners, and then you get a little bit more useful area. Here's another design for a sail. A lot of you guys have seen this one. This is a balanced lug. It has a yard, and it has a boom. So this is another interesting shape. You have a mast here. And so what happens when wind hits this sail? You basically, you have the depth of curvature line is kind of this way. So because you're holding these four corners, and the wind is hitting, you're going to get a depth of curvature like this, and it's a very efficient sail. The depth of curvature is slightly forward of center. So, in other words, there's slightly, if you bisect this line, there's slightly more area on this side than on that side. So what that means is you're not going to have an arc shape. You're going to have a little bit more like an airfoil shape. So this sail is really good for all headings. It's not really good for going tight to wind, but everything besides going tight to wind, this sail is really good. And you can adjust the tension in this corner here, and you can create more of a deeper curve in this sail. And this is called a balanced lug, and it's a really good sail. Okay, so what I've been trying to do is take a balanced lug and cut the top corner off. So that's what I've been doing. And so you get a shape like this. All right, so this is my sail. It's very similar to the balanced lug, except I basically cut the corner off, and I like this, and I added area at the top. And this corner is held with a batten. And so what does this do? It still gives you this nice. If you look at the diagonal, the longest diagonal, it's here. It gives you a lot of curvature. So because the area here is bigger than the area here on the side of this diagonal, you still have a good aerodynamic shape, and but you have more area at the top. So that is the advantage, because if you try to draw like an ellipse in here, that's kind of the useful area, and now you try to draw an ellipse in here, there's less waste. So you get waste here, you get waste here, over here, and this one you just get a little bit waste down here. So this sail does not really need any, like 3D stitching. It might need a little bit, but it's just my intuition that a sail like this would, because of its profile, because of the fact that there's less area here than there is here, that it would take on a shape that is close to the aerodynamic shape, which is important when you're wanting to go quickly into the wind. So the whole point of designing this sail was basically to take this sail, which is good except pointing into the wind, and make it better at pointing into the wind.